Deep beneath the quiet green pine forests of Washington state, massive rivers of liquid rock are shifting right now, not miles away from human cities, but directly under a ticking giant. Scientists just registered hundreds of tiny tremors deep inside the dark subterranean plumbing of Mount St. Helens. That is not a simple memory of 40 years ago, but an active recharge of fresh magma. If you want to stay ahead of the ground-shattering science breaking across our planet before the main headlines even hit television, hit that subscribe button today. Join our growing community of curious minds, where we uncover the raw, unfiltered truth behind nature's most mysterious forces. To understand why a few quiet tremors under a mountain can make world-famous geologists hold their breath, we have to look back at history. For a very long time, people living in the Pacific Northwest thought of Mount St. Helens as a peaceful natural monument. It was known for its almost perfect cone shape, covered in bright white snow and surrounded by thick evergreen trees. Many people even called it the Mount Fuji of America, because it looked so calm, beautiful, and completely harmless. That peaceful picture completely shattered in the early spring months of the year 1980. Underneath the calm snow, deep underground pressure was building up at a terrifying speed that nobody expected. Thousands of small earthquakes began shaking the ground right below the mountain peak. As molten rock pushed its way up from miles beneath the crust, it could not find an easy way out through the top. Instead, the thick liquid rock began pushing against the northern side of the mountain, creating a massive bulge. Day after day, scientists measured that bulge on the north face, growing outward by 5 feet every single 24 hours. Imagine a giant wall of solid rock and ice being pushed sideways by 5 feet every day, as if someone was inflating a balloon inside a stone wall. Geologists realized that the mountain was becoming unstable, but no one could truly predict how catastrophic the final break would be. The pressure inside was trapped, just like shaking a giant glass bottle of warm soda with the cap screwed on tight. Then came the morning of May 18th, 1980. At exactly 8:32 a.m. local time, a magnitude 5.1 earthquake shook the mountain, and that gentle shake was the final straw. The entire northern face of Mount St. Helens ripped loose and slid down the valley in the largest landslide ever recorded in human history. Removing that massive weight of rock was like popping the cork off a giant pressurized bottle all at once. The trapped gas and superheated liquid rock inside exploded sideways with unimaginable violence. Instead of blowing straight up into the sky like a standard volcano, Mount St. Helens exploded laterally across the countryside. A superheated wave of gas, ash, and pulverized rock blasted out at speeds greater than 300 miles per hour. It instantly flattened hundreds of square miles of ancient pine forest, as if the giant trees were nothing more than tiny wooden toothpicks. The temperature inside that blast cloud reached over 600 degrees Fahrenheit, instantly scorching everything in its path. Tragically, 57 people lost their lives on that single morning, including experienced scientists, loggers, and local residents. A famous volcanologist named David Johnston was standing on a ridge 6 miles away, watching the mountain through his equipment. His final words over the radio were a quick, frantic shout saying, "Vancouver, Vancouver, this is it," right before the blast swept over his post. That ridge was later renamed Johnston Ridge in his honor, serving as a permanent reminder of how fast nature can turn deadly. Did you know that Mount St. Helens exploded sideways instead of blowing straight up into the air during that famous event? Drop a quick comment below if you ever learned about that incredible landslide, and hit that like button to help spread real science to more people. When the dust finally settled after that terrible day in 1980, the entire landscape was unrecognizable. The beautiful mountain that once stood at 9,677 feet tall was suddenly much shorter. More than 1,300 feet of its rocky peak had been completely blown away into dust and scattered across state lines. In place of a majestic, snow-capped cone, there was now a gaping, horseshoe-shaped crater nearly 2 miles wide. Billions of dollars in property damage had been caused, and dark ash fell from the sky like dirty snow across several American states. For several years after the big explosion, Mount St. Helens stayed busy inside its new, giant crater floor. Between 1980 and 1986, molten rock slowly oozed out from deep underground like thick, sticky toothpaste. This heavy lava built up piece by piece, forming a massive dome of solid rock right in the center of the giant crater. Eventually, the active lava flows stopped, and the mountain seemed to settle down into a long, quiet sleep. Most people assumed the famous volcano had used up all its energy and would stay quiet for generations to come. However, volcanoes rarely stay quiet forever, and Mount St. Helens proved the point again in the year 2004. Without much warning, the ground inside the crater began to shake again, and bright plumes of steam shot high into the air. For 4 long years between 2004 and 2008, fresh liquid rock pushed its way up to the surface once more. It squeezed out into the crater floor, creating giant spines of solid rock that grew as tall as city skyscrapers before crumbling down. Scientists watched closely as millions of cubic yards of brand new rock filled in the empty crater basin day after day. By 2008, that second active phase ended, and the giant mountain went quiet once again. Ever since then, teams of dedicated geologists have kept a constant watch on the mountain using modern technology. They use sensitive seismometers buried deep in the dirt to listen for the tiny, crackling sounds of breaking underground rock. They use ultra-precise GPS units anchored into solid stone to measure if the mountain is expanding or shrinking by tiny fractions of an inch. Satellite radar systems orbit high above Earth, bouncing signals off the slopes to map any subtle changes in the ground surface. All of these tools feed raw information directly to the United States Geological Survey Cascades Volcano Observatory in Vancouver, Washington. Scientists there work alongside researchers from the University of Washington Pacific Northwest Seismic Network to monitor every twitch of the mountain. Their primary job is to spot any unusual signs long before a dangerous situation develops for the people living nearby. For a long time, the instruments recorded only normal background activity, suggesting the mountain was resting peacefully. This brings us to the first major pattern that scientists always study when monitoring active volcanoes like Mount St. Helens. Experts originally expected that after the heavy activity ended in 2008, the deep magma system would stay completely calm for a very long time. They believed the mountain would need decades of total silence to cool down and settle after releasing so much energy over the years. According to standard textbook models, a volcano that just spent years oozing rock should enter a long period of deep underground slumber. If you were living near an active volcano, would you feel safe knowing scientists are watching it 24 hours a day? Subscribe to the channel right now so you never miss an update on breaking geological discoveries, and let us know your thoughts in the comments. What was actually found beneath the volcano completely challenged those original expectations. Instead of total silence, seismometers began detecting series of subtle earthquake swarms deep beneath the mountain floor. These were not large quakes that people could feel standing on the grass, but tiny micro-earthquakes occurring miles deep in the earth. Dozens of tiny shakes were happening every single week, clustered together in tight vertical zones far below sea level. The data showed clearly that the underground plumbing system was far from being dormant or dead. Why does this gap between expectations and reality matter so much to geologists and local communities? It matters because these deep earthquakes are the direct fingerprint of a process called volcanic recharge. When molten rock deep down in the Earth's mantle rises upward, it has to force its way into tight cracks in the rocky crust. As that hot liquid rock squeezes into those tight spaces, it snaps the solid rock around it, creating small seismic tremors. This proves that brand new magma is actively flowing up from the deep earth and refilling the main underground storage chamber. To visualize how this works, imagine a giant underground storage tank buried 4 to 8 miles beneath the crater floor. When the volcano erupts, that tank loses pressure and empties some of its stored liquid rock toward the surface. Once the eruption stops, the deep engine of the Earth does not just turn off like an engine switched off with a key. Instead, hot liquid rock from much deeper down slowly pushes upward to fill that empty space back to the top. This process of refilling creates pressure, snaps ancient rock walls, and causes the earthquake swarms that scientists are detecting today. This next detail is what scientists pay the closest attention to when tracking underground pressure changes. Alongside the earthquake swarms, scientists turn to their network of high-precision satellite GPS stations to check for surface movement. In theory, if those underground earthquakes were just caused by old rock settling or cooling down, the surface ground should remain completely still. Experts expected to see zero movement on the outer slopes of the mountain if no new force was pushing from below. Once again, the actual data revealed a very different and much more dynamic reality happening beneath the forest floor. The ultra-precise GPS receivers showed that the entire mountain is very slowly bulging outward and upward by tiny amounts. While the movement is only a few millimeters each year, it is happening steadily across the entire volcanic edifice. This physical inflation of the mountain proves that the underground chamber is not just holding rock, but is building up internal pressure. Understanding this inflation matters immensely because it helps scientists estimate how much new magma has entered the system. By combining the earthquake depth maps with the ground inflation measurements, geologists can calculate the volume of new liquid rock moving in. It shows that the subterranean engine of Mount St. Helens is slowly reloading its chamber for whatever future event might happen years or decades from now. It is like watching a giant battery very slowly charging up over a period of many years. Here is the part of the story that turns standard science into an urgent mystery for the entire region. While Mount St. Helens gets most of the famous news headlines, it is actually not the only mountain that keeps scientists awake at night. Just a short drive to the north stands another massive peak known to everyone in Washington state as Mount Rainier. Mount Rainier is a towering giant that reaches over 14,400 feet into the sky, dwarfing Mount St. Helens in sheer size. In fact, many top geologists consider Mount Rainier to be the single most dangerous volcano in the entire United States. Which mountain do you think poses a bigger threat to human life? An explosive mountain like St. Helens or a massive ice-covered giant like Rainier? Tell us your guess in the comments section below, and hit the like button if you are enjoying this deep dive into Earth science. To understand why Mount Rainier carries such a terrifying reputation, you have to look at what sits on top of its rocky peak. Mount Rainier is not just a high pile of stone. It is covered in more than 2 cubic miles of solid glacial ice and permanent snow. That is more ice and snow than all the other Cascade volcanoes combined, hanging high above populated valley floors. If you took all that ice and spread it out evenly, it could cover an entire major city in a thick, frozen blanket. The central mystery of Mount Rainier comes from what is happening inside the mountain while all that ice rests on top. For hundreds of thousands of years, hot, acidic steam and thermal gases have been leaking through cracks inside the mountain core. This hot, acidic water slowly rots the tough, solid basalt rock from the inside out, turning hard stone into soft, weak clay. Scientists call this process hydrothermal alteration, which basically means the mountain is slowly digesting its own structural skeleton. This creates a serious pattern that geologists have had to study very carefully over the past few decades. Original popular belief suggested that a volcano only poses a threat to humans when it is actively shooting red-hot lava into the air. Most people assume that if a mountain is not blowing out huge clouds of black ash, the surrounding valleys are completely safe. They imagine that an eruption is the only thing that can cause destruction around a volcano. The actual reality discovered by scientists is far more unexpected and far more dangerous for local cities. Because Mount Rainier's internal rock has been turned into weak clay by hot steam, large sections of the mountain are physically unstable. A major section of the mountain slope can suddenly collapse under its own weight without any explosive volcanic eruption happening at all. A simple earthquake, a strong storm, or internal steam pressure could cause millions of tons of weakened rock and glacier ice to slide down at once. When millions of tons of hot rock and crushed glacier ice mix together, they create a terrifying natural force called a lahar. A lahar is a giant, fast-moving river of volcanic mud, boulders, and water that has the thick consistency of wet concrete. As it roars down the mountain valleys, it swallows everything in its path, including mature forests, bridges, roads, and homes. Because it is so dense and heavy, a lahar can carry massive boulders the size of houses as easily as wooden sticks in a creek. It moves at speeds up to 40 or 50 miles per hour, making it almost impossible to outrun once it reaches the narrow river channels. Do you know that volcanic mudflows can travel dozens of miles away from a peak even without a full eruption? Let us know in the comments if you have ever heard of a lahar before, and subscribe to join us for more incredible science stories every week. The historical record shows that Mount Rainier has produced massive lahars many times in the recent geological past. About 5,000 years ago, a massive section of Rainier's summit collapsed, creating what scientists call the Osceola mudflow. That single mudflow was so enormous that it traveled over 40 miles down the river valleys all the way to Puget Sound. It filled in ancient valleys with a layer of thick mud and rock over 100 feet deep across hundreds of square miles. Later, about 500 years ago, another major mudflow called the electron mudflow roared down the Puyallup River Valley. Why do these ancient mudflows matter so much to us in the modern world right now? They matter because hundreds of thousands of people now live, work, and go to school directly on top of those ancient mud deposits. Cities like Orting, Puyallup, Sumner, and parts of Tacoma are built straight on the smooth, flat land created by past lahars. More than 80,000 citizens sleep every night in zones that could be swept over if a new major mudflow were triggered today. What was once a wild river floodplain covered in ancient mud is now filled with neighborhood homes, shopping centers, and schools. Now, let us shift our view from past history to what is actually happening right now in the present day across Washington state. Underneath both Mount St. Helens and Mount Rainier, sensitive instruments are recording an ongoing story that is far from finished. Network seismometers operated by the Pacific Northwest Seismic Network continue to pick up subtle shifts deep below the Cascade Range. These microtremors are a quiet reminder that the tectonic forces shaping the western United States are constantly at work. The Earth beneath the Pacific Northwest is not frozen in time. It is a living, moving system driven by massive heat deep below. This brings us to another major pattern regarding how these volcanoes fit into the bigger global picture. People originally believed that volcanoes like Mount St. Helens and Mount Rainier were completely independent monsters operating on their own. It was commonly thought that each peak had its own isolated bucket of magma that had nothing to do with any other nearby peak. Old textbooks treated each volcano like an isolated island with zero connection to the mountain standing 50 miles down the road. Modern geological research using advanced seismic tomography has revealed a much more connected and fascinating reality. Scientists can now send harmless seismic waves through the Earth to create three-dimensional scanner images of the underground crust. These images show that the volcanoes of the Cascade Arc are all fed by a massive regional subduction zone dynamic. Off the coast of Washington and Oregon, a huge piece of ocean floor called the Juan de Fuca Plate is sliding under North America. As that heavy ocean plate sinks deep into the hot mantle, it releases trapped water and gases into the surrounding hot rock. That trapped moisture lowers the melting temperature of the deep mantle rock, causing hot liquid magma to rise upward toward the surface. This creates a long chain of underground magma pathways feeding Mount Baker, Glacier Peak, Mount Rainier, Mount St. Helens, and Mount Adams. They are all part of one vast, interconnected geological factory powered by the slow collision of giant tectonic plates. When pressure builds up along the regional subduction zone, it influences the entire chain of mountains over long spans of time. If you think this is only about Washington State, the true scale of this system will surprise you even more. The Cascade Range is actually just one small section of the famous Pacific Ring of Fire that circles the entire Pacific Ocean. This vast horseshoe-shaped ring contains more than 75% of all active volcanoes on the entire planet Earth. From the southern tip of South America up to Alaska, down through Japan and into New Zealand, this ring drives Earth's greatest geology. The same fundamental forces pushing magma under Washington are also driving volcanic activity in Japan, Indonesia, and Iceland. To keep communities safe from these powerful forces, scientists have built one of the most advanced warning grids in human history. In the river valleys surrounding Mount Rainier, emergency managers have installed networks of specialized acoustic flow monitors. These monitors are small devices buried along riverbanks that constantly listen for the unique, low-frequency vibrations of a moving mudflow. If a lahar starts rushing down a river valley, the sensors instantly pick up the heavy shaking and trigger automated warning sirens in downstream towns. This gives local residents vital minutes to evacuate to higher ground before the thick wave of mud arrives. At the same time, us volcanologists are using airborne gas sensors to measure the invisible gases venting from crater cracks. When fresh liquid rock moves closer to the surface, it releases distinct volcanic gases like sulfur dioxide and carbon dioxide. By flying airplanes through steam plumes or setting up permanent monitoring boxes, scientists can track changes in gas output. A sudden spike in sulfur dioxide emissions often means fresh magma is rising near the surface and degassing under lower pressure. This gas data gives experts a crucial second layer of evidence to confirm what their earthquake sensors are reporting. Do you think human technology will ever be fast enough to fully protect us from a sudden volcanic disaster? Share your perspective in the comments section below and subscribe to stay informed about the latest natural science developments worldwide. It is equally important to zoom out and think about why these subterranean giants matter to every single one of us. Even if you live thousands of miles away from Washington State, a major volcanic eruption can impact your daily life in unexpected ways. When a volcano erupts with great explosive force, it shoots billions of tiny particles of glass and pulverized rock high into the atmosphere. This fine volcanic ash can travel across entire continents, carried by high-altitude jet stream winds in just a few days. Volcanic ash clouds pose an extreme hazard to modern jet airplanes flying across busy international flight routes. When a jet engine sucks in fine volcanic ash, the intense heat inside the engine melts the glass particles instantly. That liquid glass then coats the inside of the turbine blades, blocking airflow and causing the jet engine to stall completely in midair. During past eruptions around the world, major air corridors had to be shut down entirely, grounding thousands of commercial flights. A major eruption in the Cascades could easily disrupt global travel, air cargo delivery, and international supply chains for weeks. Furthermore, massive volcanic eruptions can even alter global weather patterns and climate for months or years after the blast. When heavy sulfur gases reach the upper atmosphere, they react with water vapor to form microscopic droplets of sulfuric acid. These tiny liquid droplets act like a giant mirror high in the sky, reflecting a portion of the sun's heat back into space. This global cooling effect can lower average world temperatures, leading to unseasonal frosts, crop failures, and unusual weather patterns worldwide. In 1816, a massive eruption in Indonesia caused what history calls the year without a summer, bringing summer snow to North America. Studying active volcanoes also satisfies one of the deepest and most fundamental human traits, a relentless curiosity about our world. Volcanoes are nature's windows into the deep interior of our planet, offering us a rare look at the thermal engine driving Earth. Without volcanic activity over billions of years, Earth would not have its oceans, its atmosphere, or the dynamic surface that supports life. The very same geothermal forces that present danger to local valleys are also responsible for building rich soils and shaping our beautiful landscapes. Learning to respect and understand these giant natural systems is an essential part of living safely on a dynamic, evolving planet. The ongoing signs of activity at Mount St. Helens and Mount Rainier remind us that Earth is a living, changing world. Science does not exist just in static textbooks sitting on a shelf. It is happening right beneath our feet every single second. Every tiny earthquake recorded by a seismometer and every millimeter of ground inflation measured by a satellite adds a new piece to the puzzle. By paying close attention to these subtle signals, scientists continue to unlock the mysterious secrets hidden deep within the dark crust of our planet. If you enjoyed uncovering the hidden science behind Washington's most dangerous volcanoes, make sure to hit that subscribe button right now. Do not forget to turn on all notifications so you are always the very first to know when a new scientific mystery is explored. Leave a comment down below telling us which volcano story surprised you the most, and share this video with a friend who loves real science. Thank you so much for watching, and we look forward to seeing you in the very next story.